Hello everyone, and welcome to our very first Calculus 2 video lecture. In this lecture, we're going to be going over introducing section 1.1, which is approximating areas. And that might throw you off, like, why are we even talking about approximating areas? Like, didn't we learn how to calculate areas like in elementary school? Well, we're taking it back there. So, in fact, the reason why is because integrals, which remember, Calculus 2 is all about integrals and integration. And integrals are literally the area under the curve of f of x, our function, bounded below by the x-axis. So we're going to use capital A for area is equals to the integral. So this elongated s is our integral symbol. And then that's the integral of our function. And then we use a dx here to denote that it's the integral with respect to x, because x is the variable in our function, right? And so what we would also usually see is a small a or a number there, and then a small b or a number there. And these are called the limits of integration. So a is the bottom bound and b is the top bound. To put that into context, let's draw a picture. So let's say, for example, that this is our function f of x. We don't know exactly the equation for it. We're just talking generically, abstractly here. So a and b, you notice, are already on here. So that means that we want the area under the curve of f of x, which is the blue line, right? Bounded below by the x-axis, right? This is the x-axis, remember? And this is y. And so a, the integral, is equal to this area in here. So bounded below by the x-axis, on the right by b, above by the curve, and on the left by a. So just give me a minute while I fill this in. Alright, so this in here is capital A, right? That's the area. So that literal area, that literal green, whatever numeric value represents this area, that is what's given to us by our integral. So integrals are literally the area under the curve of f of x bounded below by the x-axis. So how do we approximate the area A? Right, so we do know that whatever the area is, that is equal to the integral. So eventually, right, like if we knew what the formula for f of x was, then eventually we'll learn integration formulas that will make our life easy. But before we go there, in order for you guys to get this conceptually in your head that it's calculating the area, we use geometric formulas. So use well-known geometric formulas. What the heck do I mean by that? Well, what we're gonna do is we're gonna break this shape up into smaller shapes and calculate the area of the smaller shapes and add them all up. Right, so let's say that we divided this area into two rectangles. Right, so when I choose the rectangle, so when I'm trying to make this rectangle, these rectangles here, so when I'm trying to make the rectangle, I could use various heights, right? I could use this height here to draw my first rectangle on the left, or I could use this height here, right, to draw my rectangle, or I could even use this middle point right here. So dependent on what height you use is going to depend on what your answer is going to be. So we have three options for heights. We could either choose the left point, right, like here. This would be me choosing the left point of this first interval for this first rectangle, and then I would choose the left again for the height of the second one. So when we choose the left point like that, that's called the left point approximation, and we use the capital letter N to denote that. So that means that we're going to use the left point for the height of each triangle. Sorry, I said triangle, I mean rectangle. Okay, now I'm going to use the right endpoint of each subinterval, right? So right here I have two subintervals or two rectangles. So now I'm using the right endpoint. So the notation for this would be Rn. And I forgot to mention what the N stands for. So R stands for using the right point for the height of the rectangles. And then N is actually the number of rectangles you're using. So in this case, it would be, right, this would be R2. And that is an approximation for the integral. Ooh, the lower bound is A, the upper bound is B, and then our function is f of x. So we're doing R2, right? And then the last option that we have is using the middle point here as the height. So the middle of each rectangle. And that we use the notation n for midpoint and then n again for the number of rectangles. So this is the midpoint is used of each rectangle to determine its height. Right, so what is the height of this point here, right? Remember, so whatever point this is, let's just call it x1. Remember that we can find, this is a point on our curve, right? This is also a point on the curve of f of x. So if this is x2, then this height right here is just whatever the function equals at whatever x2 is, right? And this height here is whatever the function equals at x1. So we've talked about the heights, right? We're going to use either the left points, the right points, or the midpoints. What's important is that if you use the left points, you use the left point for every rectangle. If you use the right point, you use the right point for every rectangle. If you use the midpoint, you use the midpoint for every rectangle. And that's to determine the height of each rectangle. What about the width? So remember, n is the number of rectangles, and the width of each rectangle, we actually want the width to be equal for each rectangle. That's going to make our life easier, right? Because we already have the height's already changing depending on what rectangle you are. So let's be at least consistent with the width. So the width, right, each rectangle must have equal width. And so what we have is a formula actually. So the width is equals to delta x. So the triangle, that's a Greek letter delta actually. And delta just stands for change. So the change in x, right? Because the width at the end of the day is how much we go from A up until this point C, let's call it, or from C to B. So right, that's changes in x because that's the x values. So what we do is we just take the entire width of the region for which we're trying to find the area, right? So that's from A to B. So that width we know will be B minus A. And then we're going to divide that with, we want each rectangle to have the same width, so we just divide that by n, the number of rectangles that we want. And so each rectangle has width delta x, whatever that is, right? When you're given a B and an A and you're told how many rectangles, you'll be able to plug in B, A, and N and find the value for the width. So sorry that this is all super abstract. I'm going to do an example now, and that'll hopefully bring this all together. So the example says, approximate the area under the graph of f of x equals x squared between x equals 1 and x equals 2 using 4 rectangles. And so we're going to want to compute L4, R4, and M4. Graph here is of f of x equals x squared. Remember, that's a parabola at 0. And we want to calculate the area between 1 and 2. So let's first practice writing this in integral notation. So let's call this area A. And remember that L4, R4, and M4, using the rectangles, that's approximating the area. So that's an approximation for A. An approximation for the integral between 1 and 2 of x squared. And again, we use dx because x is the variable we're integrating with respect to. That's our variable of interest. Our job is to find A, right? Or find at least an approximation of A. Which one is L4, which one is R4, and which was an M4? So let's look closer, right? So we have in this first graph, if you notice, the height of the first rectangle is whatever the value of that point is. The height of the second rectangle is this, right? So this is our second rectangle. And then the height of our third rectangle is whatever this height is. And then the height of our fourth rectangle is whatever this height is. So if we look close, we notice that that is the left side of each rectangle. So this is L4, right? This is a picture of L4. And we can see L4, right? There's some gaps in the area of A, right? A had all of this included, right? Let's look back, because remember, A is the integral from 1 to 2 of our function. And remember, the integral is the area below the curve, bounded below by the x-axis, and on the sides by the limits of integration, right? A and B, in this case, 1 and 2. So if you notice, all of this in here was included. But when we go down on L4, in this case, that area is actually missing, right? That's not included in our L4 approximation. So L4 will be what's going on? Is an under approximation of A, which is the integral from 1 to 2 of x squared dx. Right, and that's simply because we know that it's going to be missing some of the area that we wanted to include in our calculation, right? So let's go on to the next one. So for this next one, we see the height of this first rectangle is whatever this height is here. What the second one is whatever this point is here. Right, so I'm looking at the height, right? The height of this one is right here. Move that over just a smidge. Ooh. And then the height of this last one is whatever that is there. So if we notice, this is the middle point of each rectangle. So this is M4. And this is hard to say whether it's an over and an under approximation, right? Because remember, this area under the curve is missing, right? But then we have this area that's above. So that's overestimating that pink area, right? So all of these pink areas, you notice they're above the curve. Versus the yellow areas, those were missing pieces of the areas that we wanted to include in our calculation. So as I mentioned earlier, the midpoint usually gives us the best approximation out of the 3 methods, because the over areas in pink get canceled out by the underrepresented areas in yellow. So we're not sure. It's hard to, we can't say that M4 is an over and under approximation unless we know the exact value of A. But M4 is an approximation for the same integral, right? That same area from 1 to 2 of x squared dx. And then lastly, right, when we look at the height of this first rectangle, it's whatever that point is on the curve. Right, when we look for the height of the second rectangle on the curve, it's right here. When we look at the height of the third rectangle on the curve, it's right here. And the height of the fourth is whatever that point is there. Right, so these are our 4 rectangles. And if you notice, we use the right side of each rectangle, right, in order to get the height. And so this is R4, right, the right-hand approximation. So here we see that there's no areas under the curve. Ooh, there's no area under the curve that's missing, right? We have the entirety of A included, but on top of that, we also have some areas above. So this is an over approximation of A, right? Because it has more area than just A. Remember, A was just the area under the curve. Here, we have a bunch of areas over the curve. So R4 is an over estimate or approximation. Estimate and approximation, those mean the same thing. So those are synonyms. For A, which is the integral of x squared from 1 to 2. And so the reason why I wanted to do this was just to show you guys that we're just using shapes in order, right, in this case specifically rectangles, in order to approximate this area A, because we don't have a nice geometric formula for whatever shape this is. This is an irregular shape. And so we can do that in 3 ways, because we're going to use the same width for each rectangle, right? Because we have 4 rectangles in each of these examples. However, the height is going to change depending on which we choose to use. Okay, so let's start with L4, right? We know this is L4 because it's using the left side of each rectangle for its height, right? So this is L4. then what's that gonna equal? Remember, first we have to calculate all of the heights, right? So what's this height? What's this height? What's this height? And what's this height? So if you notice, right, this right here is the value x equals 1. So the corresponding height is going to be f of 1, which we know, remember that this function is f of x equals x squared, right? So we know f of 1 is 1 squared, right? Because when we plug in 1 into our function, right, it just becomes 1 squared. And that's just 1, which we could have saw here, but it's not always that obvious. So I'm going to go through it anyways. Right, and then what about this second height here? Well, what's the x value there? Right, that's the midpoint between 1 and 1.5, so that's 1.25. Remember, the width of each rectangle is the same, and we had a formula for that, right? We called it change in x, or delta x, and that was b minus a over n. And remember, b is the right boundary, so that's 2, and then a is the left boundary, so that's 1. And then n, remember, is the number of rectangles, which we have 4. So the width is 2 minus 1 is 1 over 4, so that's 0.25. So each rectangle has width 0.25. So that gives us 4 sub-intervals, right? So we start, the leftmost interval is 1, and that goes to 1.25, right? That creates our first rectangle. Then the second one goes from 1.25 to 1.5. And then the third one goes from 1.5 to 1.75. And then the last one goes from 1.75 to 2. Right, so we know that this right here is 1.75. Okay. So this was the height of the first rectangle. All right, and this is the width of each. Right, so now if you want to find the height of the second rectangle, right, we're using 1.25. So that's going to be f of 1.25. Right, so that's, remember, our function again is still x squared. So I'm going to plug 1.25 into x squared. And that's going to give me the height of the second triangle, which let's calculate that. So 1.25 times 1.25, that is 1.5625. And then for the third triangle, remember that's at 1.75, right? That is, oops, I lied. The third triangle, the right side is right here, right? So that corresponds to 1.5. So then it's f of 1.5. So let's do 1.5 times 1.5. So that becomes 2.25. And then last but not least is the right endpoint, right? Corresponding to 1.75. Excuse me. 1.75. So 1.75 squared. Let's see what that is. We could see it's around 3. And yes, that is equal to 3. Right, and so one way that I like to write these 4 sub-intervals like this, because if you notice, right, once you write your sub-intervals, which these sub-intervals are going to be the same no matter if we're doing L4, R4, or M4, right? Like this is us dividing 1 to 2 into 4 equally spaced intervals. We used the left of each of these intervals in order to plug into our function f of x, right, in order to get the heights for each of the rectangles. So that's why I find it pretty helpful to write out the 4 sub-intervals like this. So let's actually calculate L4. Right, so what we have to do is the width times the height of each rectangle. So the first height was 1, and then the width again is 0.25. The second height is 1.5625, and then the third one 0.25 times 2.25 plus 0.25 times 3. So let me just make some space here. So remember, what we could do is just pull out the 0.25, and then we just will multiply that times the sum of all of the heights. And that'll make the calculation a little bit shorter for us. Alright, so let me use my calculator. So we have 1 plus 1.5625 plus 2.25 plus 3. So I have 0.25 times 7.81. And that gives me 1.95 as my final L4. Okay, so now let's move on and let's do R4. So I'm going to do R4 next. So this was L4. So, okay. So this was our picture for R4. Right, so remember in this photo, again, we're doing 4 rectangles no matter what, remember? N is 4. So we're calculating R4. Remember that 4 means 4 rectangles, right? And then if we see the R, remember, stands that we're using the right side of each rectangle, that point, the right side point on the curve as the height of each rectangle. Right, so this is 1, this is 1, this is 1. And we already know what our intervals are, right? Because we're still doing the same from 1 to 2 divided into 4. So this is still 1.25, this is still 1.75. So our subintervals are still 1 to 1.25, 1.25 to 1.5, 1.5 to 1.75, and 1.75 to 2. Right, but now we want to use the right endpoints. So you don't always have to have a graph. If you write out your subintervals like this, it's really helpful because when you're using the right endpoints, now I want to use the right number in each of these intervals, right? In the previous one, in L4, we use the left side of each interval, right, in order to do our heights. Right, now this time we're going to use the right. Right, so we have to plug all of these values into our function, which, remember, our function that we're working with in this example is f of x is x squared. So I'm going to plug in 1.25 into f of x, and that's going to give me 1.25 squared. I'm pretty sure I did that already. Yep, that was 1.56, and then f of 1.5, right, that becomes 1.5 squared, and we did that was 2.25, and then f of 1.75, right, we plug that into our function x squared, that gives us 1.75 squared, that's equal to 3, and then f of 2, we plug that into x squared, that's 2 squared, that's 4. And now we have to make sure we set up our formula correctly. So we do R4 is equals to, right, the width of each rectangle we said was 0.25, and then we sum up all of the heights. So the heights we got were 1.56, 2.25, 3, and 4. And should we expect this R4 to be greater than L4? Yes, because remember, these are all overestimating, right? They're over the curve, so that's overestimating A. Whereas here we were missing area under the curve, right? Because remember, we're trying to calculate this area under the curve. Right, we're trying to approximate A. So here we know off the bat R4 is going to be bigger than our answer for L4 because of the way we set up the rectangles. Right, so let's do the math. So we're going to do 1.56 plus 2.25 plus 3 plus 4. And that's going to give us 10.81. And then when we multiply that times 0.25, we get 2.7. So this is our approximation for A using the right endpoints, right? This looks like a greater than, this is an equal sign. Okay. And then lastly, I saved M4 for last because it's the one that's a little bit more complicated. So let's take our picture. So here is our picture, our graph. I should be saying graph. I don't know why I keep on saying picture. Sorry, guys. So we have 4 rectangles. Remember, what is the height? What point are we using for the height when we're doing MN, in this case M4, since we have 4 rectangles? Remember that what we're doing is we're using the point in the center of each rectangle as the height. Right, so this is still 1.25, right, because we're just dividing the area into 4. Right, so our 4 sub-intervals, right, the bounds of our rectangles are 1 and 1.25, still all the same. However, now we're not using the left or the right endpoint. Now we need to use the middle point. So how are we going to find out the middle point? So there's a number of ways you can find out the middle point. The foolproof way is when you have each of your sub-intervals, you just add the 2 endpoints together, the left and the right, and then you divide that by 2. And then you can do that for each of them. So 1.25 plus 1.5 divided by 2, 1.5 plus 1.75 divided by 2, and then 1.75 plus 2 divided by 2. Remember, we're using the middle point for our height, so we first have to figure out what's the middle point here, what's the middle point here, right? We don't know what those x values are, and so let's put these all in our calculator. So these are our midpoints. These are the x values, right? These are the x values to plug into f of x for the heights, right? Because whatever the function equals, right, here we know is f of, we know that one is 1.125. That's the height of that rectangle. For the second one, what did we get? That's going to be the height at f of 1.375. Right, for the third rectangle, we got 1.625, right? So we know that whatever this y value is the value of the function x squared at 1.625. And then the last one was f of 1.875. So it matters. It's so important that you don't mistakenly think that these are your heights, that the 1.125 and the 1.375 and the 1.625 and the 1.875 are your heights, because it's not. That's the x value where the height is. So you have to plug that x value into your function, which in this case, remember, our function is f of x is x squared, in order to get the heights. So let's do that next. So to find the heights, right, plug in the midpoints into f of x. In this example, our f of x is x squared. So we're going to do f of x, right? Let's just write it here. It's x squared. So f of, let's plug the first one in, 1.125. So that's going to be 1.125 squared. And then we need to plug in, so let's do that. So 1.125 times 1.125. So that's 1.265. And then let's do the next one. So we plug in 1.375 into our function. So that's 1.375 squared, simple enough. So that's 1.89. And then we take the next one, 1.625. So we're going to plug that into f of x, 1.625. So that's 1.625 squared is 2.64. And then we do f of 1.875, right? So that's 1.875 squared. And that's 3.52. Okay, let's just round this one up for simplicity to 1.27. Okay, so then our M4, remember, our width is 0.25 for each of our rectangles. Then we're going to multiply that by the sum of the heights. Okay, so we do 1.27 plus 1.89 plus 2.64 plus 3.52. Then we multiply that by 0.25. So we get 2.33 for our M4. So that is our final answer for M4. So as you can see, M4 was 2.33, R4 was 2.7, which we know, right, this was an over approximation, so that's why it's bigger. And then this was an under approximation, and L4, remember, was 1.95, and 1.95 is less than M4, because remember, it's for L4, we were missing area, so that was an under approximation. So 2.33 M4 is the best approximation for A. And so that's pretty much the idea behind approximating areas, is that we're going to break up weird shaped areas into equally spaced rectangles, and we add up the area of each of them in order to approximate the area, which is literally the integral. So I'm going to need you to not overthink when you think about an integral, right? This notation looks fancy, but really all it means is this area in here. All right. Thank you guys, and I'll see you in the next video.